So we're going to talk about section 3.6, which is inverse trig functions. And we've talked about this before. All right, so if I plug an angle into sine, I get out a ratio. I take that ratio, I plug it into sine inverse, and I get out an angle. Okay? And for the calculator to be able to do that, we had to restrict our domain, restrict our range, so that we only got out a one-to-one function. So we put one thing in, we get one thing out. Well, the reality of the world is that periodic functions keep oscillating, keep moving, and we have multiple points of intersection. So sometimes we want to get out all the angles. And to do that, we define something called arc cosine. Now that we have radian measures, we're going to do something where we get all of the angles back. All right? So, here's our question. For what values of x does y equal 2.5? So you can see we have our axis down here. This has a horizontal or vertical shift. And where I'm crossing 2.5 are all these points here. And the book has three methods that you can go about this. The first is graphically, second's numerically, and the last is algebraically. And the first two, graphically and numerically, are okay. But the algebraic one is the one we're going to spend the most time on and is our most accurate. Okay? Problems with graphs, you can see even here I have a thick line. It's hard to tell exactly where things are intersecting. But our algebraic method is going to be the one that really gives us our numbers that we can use that are spot on. All right. So if I take my sinusoid and I put an equation to it, can somebody explain to me where the 3 comes from? Somebody said it. It's my vertical shift. So my sinusoidal axis has gone from here, it's gone up 3. That's the middle of my graph. All right. And what's the amplitude? It's just 1. I haven't stretched it. There's no vertical dilation. All right. The 4 affects the period. And then that 2 is my horizontal shift. Okay. So if I want to know all the places where it's equal to 2.5, instead of having two variables where I have an x and a y, I now have this whole thing set to 2.5. All right. Well, these are all the points of intersection. I have the red and the green. Can anybody guess as to why I differentiate between the red and the green? Why I have two sets of colors on the points? Yeah.
Red's going down and green's going up.
Okay. Good. So green is coming up, red's going down. What is that distance in terms of the graph? It's a full what? Cool. Yes, rotation or period. Right. So we have, this is pi over 3. It's divided into thirds, so there's pi over 9, 2 pi over 9. I bring my point down. I can see it's somewhere between 2 pi over 9 and pi over 3. And so we could guess at 2.8 pi over 9. That's a guess. It's an educated guess, but it's still a guess. So the 2.8, if it was 3 pi over 9, what would it be? Pi over 3. So I'm saying it's close to that, but not exactly. All right, so there's my graphical solution. Easy. Right? I just looked at it and I guessed something that makes sense. So now we can do a numeric solution. We plug it in. So I take out the x and I put in 2.8 pi over 9. So 3 plus cosine quantity 4, 2 pi over 8, 2.8 pi over 9 minus 2. Plug in the calculator and I get 2.42. If I'd done it exactly right, what would I have gotten out? 2.5. So now the question is this close enough? Well, we don't really know. And if you plug this in your calculator and ask it to solve, it will graph this, it'll solve it for you. Your calculator isn't very bright, but it's really quick. And so all it does is basically it guesses a number, it plugs it in, it sees if it's close enough, It takes that, it plugs in a different number, and it keeps that iterative process going until it gets to whatever tolerance is of 2.5. But for us, we don't know if this is close enough. So we have to step back and we have to figure out, all right, how can we do this algebraically? All right. Well, there's a period, and it's repeating. So if I found this first red value, could I find the second red value? How? I'd add a period, and I can figure out the period because I know that 4 there, right? It's 1/4 of 2 pi. All right? So if I found 1, I could find all the red ones. I would just add a period to it. And in terms of what I have, my guess would be plus 2 pi times n. So, or I'm sorry, pi over 2 times n. So I'm just adding that period to it. I could get it that way. But I don't have the green ones. And so we'd have to do the same thing. I'd have to come back. I'd have to guess something. I'd have to plug it in, see if I'm close enough. Then I have to add the period to it and get all the solutions. All right, so it's a mess. And it's not very accurate. So we're going to focus on the third one, which is algebraically. All right? We good so far? Okay. So let's solve it. So instead of y, I'm interested in when it's equal to 2.5, right? All right? I want to get the x by itself. I want to solve it like you guys have been solving stuff since 6th, 7th grade. I want to use inverse operations. And I want to go reverse order of operations. So the last thing you would do, according to PEMDAS, right, would be to add. So I would subtract 3 from both sides. And I get this. So now I have to deal with the cosine. I have to undo that. Well, how do we undo cosine? Cosine inverse. Now the problem with that is if I just use a cosine inverse, how many values of x is it going to give me? Just 1. And we know from the picture that there's infinitely many. So we're going to have to rectify that. I will just get 1 using cosine inverse. We want to get all of them back. So we talk about this picture here, called arc cosine. Remember, we talked about radians as an arc length over a radius. And what's nice about cosine is these 2 points in blue here, are they going to have the same cosine value? They are, right? I'm coming out this way. So it's there and there. So I get plus x and minus x. Just like over here on the warm-up, we had plus 60 degrees, minus 60 degrees, same cosine value. So that's all we're doing. I could get all of the coterminals with x, all of the coterminals with negative x. And that's going to be all my angles. So we define this as arc cosine. All right? So arc cosine is similar to cosine inverse. It actually has cosine inverse in it. But it's giving me all the possible angles that it works for. So I have plus or minus cosine inverse as we defined it before. So our calculators, cosine inverse plus 2 pi n. And what's the 2 pi n doing for me? It's just moving all the way around the circle. So it's giving me 1. All right, this one's theta. And then if n is 1, I go around once. If n is 2, I go around twice. If n is negative, I go around the other way. Okay? So that's all the values. So we're going to use that. It's just going around. Gives all the angles. Which on our graph is the red and the green solutions. Okay. So if I apply our cosine, why did the cosine drop out? It dropped out because it's an inverse, and they undo each other. That's why I did it. All right, so I'm left with what was in the parentheses, and I have this over here. So now we just apply our definition. Arc cosine is equal to this. Cosine plus or minus cosine inverse x plus 2 pi n. All right. Well, now it's pretty much solve. Why do I say that? It's just algebra from here. And this is something we've used before. Cosine inverse. We can use our calculator. We can use our knowledge of the unit circle. Joey, question or stretching?
No. What if you, so let's say you have an amplitude, would you divide that before you go to
If I had something here in front?
Yeah.
Exactly, yeah.
So you just, right.
Yeah. So you would think about your order operator. So you multiply next, you undo that multiplication, and then you take the cosine, or cosine. Good question. And you're going to have ones that look like that. All right. So I have algebra now. I start plugging through it. It's kind of like the quadratic formula, right? You get plus or minus something. So how many solutions am I going to get? At least 2 with the plus and the minus. And then any values of n that I want. So my next step is I divide the whole thing by 4. And I add 2. So those are my values of x. That's my algebraic solution. That's everything. Those are all the red dots. Bless you. All the green dots in a form that we can solve using cosine inverse that we defined before. Yes, Laura.
How could you just add 2 if they're in parentheses?
Okay, so I divided by 4,
Right.
and then I had x minus 2. What's that?
You don't have to factor out the 4.
Nope, it's already factored out. If it was no parentheses here, then I'd have... Yes. Nope.
Yeah.
I could do that too. Do the same thing. If I had 4x minus 8, I would add 8, and this would all be over 8. Katie, question?
Yeah, the 0.5 is negative before. Does that go away when you define it?
Yeah, well, you guys are, yes. Okay, so I spent 30 minutes on Friday trying to figure out where my mistake was. Because what I should be able to do is my 2.8 pi over 9 that I thought was a guess, I should be able to figure that out by putting in a value of n, and I couldn't do it because I forgot that minus. So it should be minus, otherwise it doesn't work. So I put it back in there somewhere. So make these negative. I'll make them negative in a second. So what we should be able to do, and I won't always ask you to do this, but we should be able to find the point that we guessed. So this was our point. And when n is negative 1, I get out 0.95. And our guess was 0.98. So this is when I was guessing graphically. Let's see, I put it back in. So if you miss a negative, you're going to be getting it wrong, which is why you want to try to check your work. All right? And if I wanted the next one, so let's say I'm cool with 0.95, what do I have to add to get to the next red dot? The period, right? Okay. So it looks like a big complicated mess. It's not trivial, but all we're doing is going from something where we just get one angle back, and I want all the angles. Okay? Yeah, Joe.
So what do you do with the n?
The n, if I want to find an actual number, let's say it gives me, find 5 values. Okay? I can plug in n equals 1, 2, 3, 4, 5, and evaluate it and get it out.
Correct.
If I want all of them, this is all of them. But if I want a specific one, let's say I want the first solution where x is greater than pi. I'd have to plug in a value of n until I got something for x that was greater than pi. Or if I wanted the first negative value, I wanted this one, I'd have to figure out what value of n would work for it. Now you could solve for n. Let's say you put in a value of x, and you wanted to solve for n, you could do that. Because cosine inverse of this is just a number. So you could go that way. That was another question. Yeah, Mark.
So is it kind of just like a guess and check thing? Like you just plug in values until you find the right answer or what you're looking for?
The first one is a guess and check. If you're just looking at the graph, is basically guess and check. If you're solving it algebraically, so like this expression here is not guess and check. This is algebraic. What I was trying to do is to figure out how good was my guess. My guess was pretty good. I was 3/100ths off. So you can use the graph to get a sense of what's going on. More often than not, though, you're going to use the algebraic method and find an exact answer. Yeah.
For a test, are we going to have to use this method, or will we have to know the other ones?
The graphical and numerical? No, not explicitly. I might give you, what I would probably do, the hardest I would make it would be to give you this. Somebody guess this number. How close is it? And you could figure out the actual solution. Oops. And you could figure out that's 3/10 good, or 300 good. So I would give you a guess. If I wanted, I probably won't, but I would give you something like that. I'm not going to ask you to look at the graph, but you could check your work to see if it was appropriate. More likely than not, I'll give you something kind of what Joey asked of, give me the first 5 solutions. And you plug in values of them. Okay. Now, there's a subtle thing to pay attention to when you're writing these equations. Have we defined arc sine? No. So if you go back to this graph and you write it as a sine curve, you can't do this. Plus or minus cosine of that. Alright? It doesn't have the same property. So you can write it as a sine curve, but you can't do plus or minus the value. You would have to do something kind of like we have on the board here. This is cosine, which is nice. It's plus or minus because it's all the angles. If you use sine inverse, though, so all this is saying is plus or minus cosine inverse of the ratio is all of these angles. So that's why we're using arc cosine. Sine doesn't work quite the same way because I have to flip it over the y-axis and I get pi minus theta. So you could do it, but you would need to evaluate 2 different things. Instead of just plus or minus, you have this angle and pi minus. So it's a little bit more tricky. That would be something they would ask you like as a bonus question on a test. You could do it in terms of sine. But what you're going to need to do, and the way that the book expects you to do it, is from now on, if you're solving for something, are you going to write the equation as a sine curve? Because you don't have arc sine to deal with it. So everything's going to be a cosine curve, which is fine. You can always write them as a cosine curve. But be aware, if you start writing them in sine curves and applying the arc cosine, it's not correct. All right? Okay.